Uh, in the last class, we actually went to some extent of detail into the KNN algorithm. We saw how the K nearest neighbors works. We saw the different steps to create K neighbors. We also saw the different distance metrics that are used to come to evaluate the distance, and uh, some advantages and disadvantages of the KNN method. Let me quickly summarize what KNN method is. KNN method is K nearest neighbors, which goes with the idea that if you are close, okay, wait, this is if you are similar to your neighbors, then you are one of them. Okay, if you are similar to your neighbors, then you're one of them. And what we do in this method is in the training phase, we keep all of the data saved. In the testing phase, or in the prediction phase, we will take the new test data, evaluate its distance from all the other training elements. Once we have the distance, we will choose the top 5 or top K neighbors, which are closest to our prediction point. And we'll find out what is the class of those neighbors. And based on the class of those neighbors, we'll give the class to our prediction point. Okay, and that is the procedure for doing K nearest neighbors. Yesterday, we also saw some metrics that can be used for evaluation of if our model is doing good or not. We looked at metrics like accuracy, precision, recall, combination of precision and recall, that is F1 score, and then again combination of precision and recall with giving priority to either precision or recall. We called another metric called as F beta score. Okay. So these are common elements that help us to identify if our model is doing good or not. Okay. As I said earlier, we will first consider all the different models that we want to look at. Once we have the models, we'll then try and implement it on our Titanic dataset and see how things work out. Now, we need not worry too much about how these models will be implemented. Okay, there are many packages like scikit-learn and others which help us to implement these algorithms in our code. We need not code them out. Okay, but if we understand how they work, then it will be very useful for us to choose which algorithm will work best for our problem situation. Okay. There is this one more part regarding how the training set, validation, and test set work. And after some pondering, what I've thought is when I will explain how we will be doing validation within the Titanic set. So just before entering into the system, I'll discuss about these methods. Okay. First, I want to cover the other algorithms, and then later in one go look at the different evaluation ways. That is, what is training set, what is validation set, what is test set, what is cross validation, stratified cross validation, and so on. Okay, so I'll be covering that together once we finished our 3 more classifiers that we are going to look at. Okay. Now we are moving towards the next classifier. So we have already seen one classifier. Okay, K nearest neighbors. We are moving to the next commonly used classifier called as naive Bayes classifier. And what I want you to do is when I'm teaching or when we are discussing regarding naive Bayes, try in the background to compare it with KNN. See how KNN works on the same problem. See how naive Bayes works on the same problem. What is their approach for identifying that subsystem? So if you remember, when we started off, I said machine learning is basically trying to figure out what is there inside this box. Okay, we have different inputs, x1, x2, xn going into the model, and we have an output coming out of the model. And all the different machine learning algorithms are trying to figure out is how I can represent this system. So when we start talking about naive Bayes, in the background, also try to think how KNN is solving the same problem and how is naive Bayes different. Okay. So with that said, let me not waste a lot of time and enter into naive Bayes and see how things work out. Okay. So the naive Bayes classifier basically works on Base Theorem. Okay. Now some of you may have taken, I think when I was doing my 11th and 12th standard, that is after my SSC, when I was doing my intermediate, then I was exposed to Base Theorem. in context of probability, okay, especially in context of evaluating something called as conditional probability. It was introduced to Base theorem. Now I understand that many of us, we come from different backgrounds, and you may or you may not have heard of Base theorem. Nonetheless, naive Bayes, it works on Base theorem. I will give you a definition of what Base theorem is and how it works out. Now, it is called naive Bayes because of an assumption that we take while evaluating the Base theorem. Okay, there is one place where we take an assumption. That assumption is good or bad depending upon the situation. But if you take that assumption, you are naively assuming something, and hence we call this classifier as naive. Okay, does anyone know what is the meaning of naive? Okay, let me say. So the way I understand it, naive means plainly or simply or stupidly. Okay, sometimes without understanding the consequences, when you take a decision, it is called as a naive decision. Okay, so naive Bayes is basically, it is called naive Bayes because for one of the steps of Bayes theorem, we are evaluating something using an assumption. And since we have not verified if that assumption can be true or not, we call it a naive decision. And hence it becomes the classifier is named as naive Bayes. Okay. The advantages, naive Bayes is very easy to build, just like KNN. It is not very complex. You can easily code it out. And another advantage is it is very useful for large data sets. We saw KNN will not be very good for large data sets because as our data set increases, your prediction point, you have to evaluate the distance from all the points. So when you talk about deploying it to low powered devices like smartphones or smartwatches, then KNN may not be a very good solution. But we see here that naive Bayes, in fact, is very, very useful for large data sets also. So this is just an introduction of the classifier. Let us go deeper and see what Bayes theorem is. Okay. So Bayes theorem is basically this formula. Okay. Now within this formula, you see multiple terms. First, I will read this formula, telling you how to read something like this, and then we'll look at the different terms that make this formula. Okay. So naive Bayes or the Bayes theorem basically says that the probability of an event A given event B is equal to the probability of the event B given event A multiplied by the probability of event A divided by the probability of event B. Okay, I'll read that again. The probability of a given event of an event A given event B is equal to the probability of the event B given event A multiplied by the probability of event A divided by the probability of event B. Okay. Now, in this, I am guessing that many of us will be very familiar with something called as probability of event A or probability of event B. These are called as prior probabilities. So if I give you an example, if I say, what is the probability of getting a heads when you toss a coin? Okay, do you know what the answer to this is? Okay, excellent. What is the probability of getting the number 3 when you roll a dice? Okay, excellent. So I'm guessing since not many of you, some of you are answering, I'm guessing that you guys know what probability is. Probability is basically, if I have a sample set, I will look at my favorable conditions, and my favorable conditions divided by my sample set is my probability. So let me give you an example. If I toss a coin, there are only two options. Okay, I will get either a heads or a tails. And my question was, what is the probability that it is a heads given once I toss a coin? Okay, so out of the two options, my favorable option is 1, so I put that in the numerator. My possible options are 2, so I put that in the denominator, and I get with the probability of 1 by 2. When I ask the question, what is the probability of getting a 3 when you roll a dice? So my possible options are 1, 2, 3, 4, 5, 6. My favorable option is 3. So I'll put number of favorable options divided by number of possible options becomes 1 by 6. Had I changed my question and said that what is the probability of getting an even number when you roll a dice, then my favorable options are 2, 4 and 6. That is, number of favorable options are 3 divided by total number of options are 6. That gives me 1 by 2. So this is very simply called as probability. It is not a very complex topic. It's basically just evaluating your favorable options divided by your number of options. Okay, we've got some formulas to do that. After we have certain base probabilities, how can I take two events and get the net probability and so on? We'll talk about that sometime later. For now, we have seen what these prior probabilities are. Many times my students find it difficult to understand what do you mean by these things. Okay, what is this line in between? Why there are two numbers inside? So these are called as conditional probabilities. And what conditional probabilities do is they are finding the probability based on multiple events. Okay, so here we have an event B and we have an event A. What this basically means is what is the probability of event B such that we understand that event A has already happened. Okay, once event A has already happened, what is the probability that event B, how will the probability of event B change? Okay, when I talk about this probability of event A, I'm just looking at event A, I'm not looking at anything else. When I'm looking at probability B, I'm just looking at event B, not anything else. But when I look at B slash, or what do you say, this is a pipe actually, it's a pipe. When I look at B pipe A, or it is said, what is the probability of B given A? So the probability of B given A is, we assume event A has already happened. How does event A change event B? And then we find out what is the probability of event B. Okay. So let me probably give you an example. Okay, let's say event A is okay. Let's say I have a box, and within that box I have 3 red balls and 3 green balls. Okay, I have a box with 3 red balls and 3 green balls, and event A is once you put your hand inside the box and you remove you remove a ball outside, and that ball is red. Okay, let's say a simple example. If I fetch a ball out of this box, what is the probability that the ball is red? And this is what I call as event A. Fetching a ball outside is an event A. Fetching the first ball outside is event A. Fetching second ball outside is event B. What is the probability that that A is a red ball? Okay, so we will do the same thing. We will say if I fetch a ball from inside this box, I'm assuming when you're fetching, you cannot see. Okay, you cannot see which color ball it is. So you put your hand inside and you remove it out, and then you see, okay, it is red or green. So the probability that the ball is red is number of favorable options. So I have 3 favorable options divided by total number of options, that is 6. So you say the probability of event A is 1 by 2. Excellent. Okay. Now the second event, probability B. B is removing the second ball outside. Okay, so putting your hand inside the box and removing a second ball. Now the question is, what is the probability of event B? Okay, so the probability of event B, okay, just event B, is that I put sorry, what I said. Let me rephrase it. Event B is putting your hand inside and getting a ball that is green in color. Okay, getting a ball that is green in color. Now, in this case, since event B happens after event A, there are 2 different possibilities. Okay, one possibility is, let's say that event A removed a red ball. In that case, my number of favorable options are 3. My total number of options are 5, because now I don't have 6 balls to start from. I have only 5 balls. So this will happen if event A removed a red ball. If event B had removed a green ball, then my favorable options are only 2 divided by 5. Okay. So now we see that the probability of event B, which is the probability, which is basically drawing the second ball out, and the second ball is green. That is the probability of event B. And now we see the probability of event B can be different things depending upon probability of event A. Okay, so we need to find a different way of representing this. Okay, nonetheless, I think I'm getting too deep into the probability, conditional probability. What I want to explain is conditional probability is evaluating the probability of an given event A, given that event B has already happened. Now, evaluation of this probability is not very straightforward. We have to do certain tasks. Base theorem helps us to do that. Base theorem says that if I want to know the probability of an event A, given event B has already happened, I can do that by saying, what is the probability of event B given A has happened, multiplied by probability of A, divided by probability of B. So this is your basic base theorem, and then we'll say, how do I evaluate this? So we will look at that inside our naive Bayes classifier. Okay. Now the question you would ask is, okay, this is all interesting in evaluating conditional probabilities, but how does this help me to create a machine learning algorithm for classification? Okay, how is this useful? Okay, so I'm glad you asked. Let me go ahead and show you how naive Bayes will work out. Okay. So the task of any classifier is basically looking at the data and learning from the data certain patterns that will help it to understand the underlying target function so that we can predict for new scenarios. Okay, so keep that in mind. And for naive Bayes, let us define certain terms. Let's say that we have D training examples or training tuples. Okay, we have D training tuples. So the way you would understand is, I have multiple rows and columns. The columns tell me the number of features. The rows tell me the number of examples. And I have 1, 2, 3, like this. I have D such rows. Okay, so I have D training tables. Sorry, yes, D training tuples. And each of these tuples are called as x1, x2, x3, x4, and so on, till xd, of course. So these are capital. Let me write them out. Okay, so capital X1, capital X2, capital X3, XD. Now each tuple is represented by an n-dimensional attribute vector. So this X1 is actually this entire row. It is made up of multiple columns. These columns are called as small x1, small x2, small x3, small x4, and so on till small xn. Okay, that is how many features we have. And finally, there is a class variable. So my final target is the variable y. This variable y can take multiple options. It can take the options C1, C2, C1, Cm, and so on. Let's understand that there are m different options, okay, which the target variable can change. Now, to put it in an example, you remember Titanic dataset? Titanic dataset has only 2 options. Okay, either either survived or not survived. So we have only C1 and C2. We don't have C3, C4, Cm. Okay. If you remember the iris dataset, that is the flowers that we saw when we were explaining matplotlib for our plotting environment, we saw that there were 150 examples and there were 3 kinds of flowers. Okay, class 0, 1, and 2, I think, which stands for Iris virginica, Iris setosa, and Iris versicolor. Okay, 3 genes of flowers. So that was C1, C2, and C3. Okay, so those are the terms that we'll be using. Capital X to tell you about an example, small x to tell you about within that sample what are the features, and C to tell about the class variable. Okay. Now, naive Bayes says that when I have to evaluate these 2 conditional probabilities. Okay, let's say I have just 2 classes, C1 and C2. I have to evaluate what is the probability of C1 given a particular x. and what is the probability of C2 given a particular X. And once I evaluate these probabilities, okay, once I evaluate these probabilities, I can see which one is greater or which one is lesser. And depending upon that, I can predict the answer for this data. Okay, to put that in perspective, let me compare this with the iris data set. Okay, so it says the probability of a flower to be versicolor, okay, to be iris versicolor, given the different features. So the different features we have is, we have the features sepal length, sepal width, petal length, petal width. So we have to find what is the conditional probability that this flower is of the class versicolor, given that I have some length, some width of the sepals, some length and some width of the petals. Okay. Secondly, I would say, what is the probability? Let me copy this and paste it so that I don't have to write it again. And I change this to Setosa. And I create one more copy. And I change this to Virginica. Okay. So once we evaluate these three probabilities, okay, probability of the flower being versicolor given this data, probability of the flower being setosa given this data, probability of the flower being virginica given this data, then I can compare between the three and tell which color it was. So which gene of flower it was. So if I put this probability, let's say it comes out to be 0.3. This comes out to be 0.1. This comes out to be 0.7. Okay. Then with some level of confidence, I can say that given this data, my flower is Iris virginica. Okay. I hope this makes sense. Okay. So this is what we are trying to do here. Once we evaluate the probability, we can then use that probability to make a prediction regarding our flower. Let me go ahead. The next interesting question you should ask is, okay, this seems very interesting, but how do I evaluate this number? Okay, excellent. To evaluate this number, we will use Base Theorem. Okay, so Base Theorem says that the probability, let me now restate this statement with terms that are familiar to us in terms of machine learning or data science. Okay, what is the probability of a given class? So what is the probability of a class given a certain data such, and it says, Base Theorem says that the probability of a class given data is equal to the probability of that data given class multiplied by the probability of that class divided by the probability of the data. Okay, let me state that again. The probability of a class given data is equal to the probability of the data given class multiplied by the probability of a given class divided by the probability of a given data. So this is what we are trying to evaluate. Okay. Now, what is the probability of a given class? Very simple. Let's say if I have, for the iris data set, I know there are 150 instances, 150 different data points. Okay. I have 50 data points for virginica, 50 data points for setosa, and 50 data points for versicolor. Okay. What is the probability of one of the data points being virginica? Can you tell me this answer? Okay, okay, great. 50 by 150. Excellent answer. Okay, so the probability of a given flower, so out of 150 examples, the probability of that flower being versicolor is number of favorable options. So total number of favorable options, 50. Total number of options, 150. So 50 by 150 is the probability of this class, which is 1 by 3, as some of you are simplifying. Excellent, right? So we know how to evaluate the probability of a class, because the probability of a class does not take into account the data. I am not comparing sepal length, sepal width, petal length, petal width. I'm just commenting out of the total number of examples, how many examples are favorable to us. Okay, and that is the probability of a given class. Someone is asking, describe the formula with example. Yes, I'm going to do that. But before going to that example, I want to first discuss the formula. Okay. In the next part, just the very next slide, we will be looking at the data, and then we'll be looking at this formula, and we'll see how to do things. Okay. But for now, this is how we can evaluate the probability of a given class. Let me then tell, if we have this formula and we have this data, let me show you one more explanation of this. Okay. That means, let's say I have to compare between the probability of versicolor and the probability of virginica. Okay. The way I will write that is, I will say the probability of virginica given data. Okay. And let me compare virginica with setosa, and the probability of setosa given data. Okay. What is the probability that a flower is virginica given some data that I have? And what is the probability that the flower is setosa given some data that I have? So to evaluate this, I will use Base Theorem. Base Theorem says that this can be evaluated by saying the probability of data given that the class is virginica multiplied by the probability of the class being virginica divided by the probability of that data. And for setosa, I will write the formula, the probability of the data given the class is setosa multiplied by the probability of the class setosa divided by the probability of the data. Okay. Now in these two terms, term 1 and term 2, after I evaluate, I have to put a sign in between. Okay. I can have this side greater than the other side, both sides equal, or the right side greater than the left side. Okay, these are my three options. Okay. Now, to evaluate these three options, okay, can you probably tell me, is evaluating P of X important or not? Can I still get this? Can I still choose what is the equality without evaluating the probability of P of X? Okay. So you can say yes or no. Oh. Okay, sorry. I think I phrased the question in two different ways. Okay, excellent. P of X, no need. Now I understand. Okay. So even if we don't evaluate P of X, still we can decide these signs. And the reason is simple. I divide both sides by P of X. So this gets cancelled, this gets cancelled. Now I can directly get my answer by evaluating this term, the numerator. From the numerator, we know how to evaluate this part. That is the probability of a given class. We just saw an example of that. Okay. The interesting thing and the difficult thing is to say, how do I evaluate the second part? How do I evaluate the probability of a given data X, probability of X, given that I have a class? So that is what we do here. So it says the probability of X given a class is equal to this big symbol, which is a big pi, which goes from k is equal to 1 to n. Have you seen this symbol before? Okay, yes, excellent. So amazing. And so when I say you've seen the symbol, I also mean that not just the symbol pi, but you understand what this symbol here does. Okay. But let me explain to you something that people, product, excellent. No, yes, it is not summation, it is product. Let me show you an example of summation, and then I will show you an example of product. No, it does not add all the observation. Summation adds all the observation. If I have a symbol like this, sum, k is equal to 1 to 3, and I have k here, what I mean is this translates to 1 plus 2 plus 3 is equal to 6. Okay. If instead of k, I have something like this, I have x subscript k, then this symbol is a sigma symbol. It is called summation of k from 1 to 3 is equal to, of x of k is equal to x1 plus x2 plus x3. Now, many of us are familiar with this. Okay. There are some people who may not be familiar with the second part. Okay, the second part is the pi sign. Okay, and pi stands for product of. So instead of this symbol, instead of the first symbol, if I replace with this symbol pi, okay, then my formula will change. Instead of addition, I will have multiplication of x1 with multiplication of x2 with multiplication of x3. Okay, so the product symbol here says the multiplication of the individual terms as k changes from the initial value 1 to the value 3. So in this case, we are saying that the probability of this big X, okay, the probability of one sample given a class is equal to, just give me a moment, someone is at my door, I'll be back. Okay, sorry. So the probability of a capital X given a class is the product of the probabilities of individual elements or individual features given a certain class. Okay. So in my example of, let's say, evaluating probability of this, evaluating the probability of data sample given the class Virginica is equal to the probability of sepal length given class Virginica multiplied by probability of class sepal width given Virginica multiplied by probability of petal length given Virginica and probability of petal width given Virginica. Okay. So what we have done is we have said that let me take my capital X. My capital X is made up of small features x1, x2, x3, x4. Okay. Now x1, x2, x3, x4 for our iris data set is sepal length, sepal width, petal length, and petal width. Okay. So here we say the probability of just 1 second. The probability of sepal length given the class Virginica multiplied by the probability of sepal width given Virginica, petal length given Virginica, petal width given Virginica. So this term can be evaluated by doing something like this. Now the problem is with probabilities, we can only multiply individual events with the probabilities if they are mutually exclusive. Okay. So if the events are mutually exclusive, then we are allowed to do something like this. But if events are not mutually exclusive, then this formula, this conditional probability cannot be evaluated this way. Okay. And since in our case of naive Bayes, we are not looking at if the features are correlated or not. We are directly saying that they are mutually exclusive. So this is an assumption we are making. And because of this assumption that we make, we say that the classifier is called naive. Why? Because we are taking the assumption to evaluate the conditional probability. We are assuming that the different features are mutually exclusive. Only then this formula holds true. Otherwise, this formula is not right. Okay. So this is just talking about the nuts and bolts of how naive Bayes works. Let us get more context. As one of you was saying, show us an example that will make sense. So let us go to this example and we'll try to make some sense of this example. Okay. So first I will show you the data. Assume that we have a data like this. Okay. How many points do we have in our data? We have 8 points in our data. So 8 sample points. How many features? We have 1, 2, 3, 4. We have 4 features and we have one target class called as flu. Okay, so this is an example of a medical data. We have the 4 features: chills, runny nose, headache, and fever. So what this data basically means is, if someone has the chills, okay, if someone is feeling very cold and they do not have a runny nose, their headache is mild, and they have fever, yes, for fever, then they do not have flu. Okay, let me look at the next data point. Next data point: someone has chills, they are feeling very cold, they have a runny nose, they do not have a headache, they do not have a fever, then we say they have flu. Yes, they have flu. Okay. So what this data is doing is, it is taking the individual features like chills, runny nose, headache, and fever, and based on these features, it is trying to predict whether someone has flu or not. Okay. So we have this sample data of 8 points. Chills can take 2 values, yes and no. Runny nose can take 2 values, yes and no. Headache can take 3 values: no headache, mild headache, strong headache. Fever can take 2 values, yes and no. And finally, a target class can take 2 values, yes and no. So our task is, we have to use this data, and using this data, we have to predict for this unknown case, the test case. For the test case, we have the example that chills is yes, runny nose is no, headache is mild, fever is no. What is the prediction? Do we say that this person has flu, or do we say that this person does not have flu? Okay. Now what we'll do is, we will use naive Bayes to evaluate this answer. Okay. But for naive Bayes to work, we need to know what all these probabilities are. Okay. So we'll start with evaluating these probabilities. So very quickly, I will ask you certain questions, and you try to answer the best you can. Okay. And then if many of you are saying it wrong, then I will explain how to evaluate it. Okay. So question number 1, what is the probability of flu being yes? Okay. What is the probability of flu being yes? Okay. Can someone answer this? So this is the probability of the target class. Same way as we evaluated the probability of Virginica, we are now trying to evaluate what is the probability that flu is yes. So we have to look for our favorable conditions divided by all of our options. Okay, 5 by 8, 5 by 8, 5 by 8. Okay, excellent. So just one person answered wrong, 2 by 4, but apart from that, I've got 4 right answers. Let me tell you how to do this. Okay, so I see how many samples do we have. So we have 1, 2, 3, we have 8 rows. So my denominator will be 8. I have 8 samples. Okay, what will be in my numerator? So numerator asks, how many favorable conditions do I have? So I have 1, 2, 3, 4, and 5 yes. Out of 8 examples, I have got 5 yeses. So I will say the probability of flu as yes is 5 by 8. Okay. Similarly, what is the probability of flu as no? 3 by 8. Excellent. So we'll put it as 3 by 8. My favorable conditions are no. So I have 1, 2, and 3 no's divided by my total number of conditions, 8. So I'll say my probability of flu as no is 3 by 8. Okay. So this was the easy part. Okay. This was the conditional probability part. Let us go for something more complex. Okay. What is the probability of this thing? What is the probability that chills is yes, given that flu is yes? Okay. What is the probability that chills is yes, given that flu is yes? So many of you are answering 4 by 8. Okay. No, 4 by 8 is wrong. And let me show you the first example, and then it will make some sense. Okay. One person has answered it right. Okay. One person. Okay. I think so. I'm not sure. Let me see. So here for this example, we have to first do event A. So this is probability of chills as being yes, given that a person has flu. So when I say given that the person has flu, my sample set limits to only these examples. Okay. When it is yes, yes, and yes. Okay, just 1 second, I'll be back. My daughter has woken up. Just 1 second. Sorry. There's no one in the house, and my daughter, who is 1 year, 8 months old, is crying, so I had to hold her. Okay, let me come back to the problem. So, when we're trying to evaluate probability of chills as yes, given that someone has flu, my sample set is limited to only those examples where I have yes. Okay, so how many examples do I have? I have 5 examples of yes. So my denominator will become 5. Now, within this sample set, what are my favorable conditions? My favorable conditions are flu as yes. So I have 1 example of flu as yes, 2 examples, and 3 examples. I've got 3 examples of flu as yes. So this term can be evaluated by 3 by 5. Okay. I hope you understand how to evaluate. Now let me ask you the next question. What is the probability of chills as no given flu as yes? What is the answer for this one? What is the probability of chills as no given that flu is yes? Okay. No, many of you are answering it wrong. Again, let me say. See here, the probability of chills as no given that flu is yes. So my sample set is how many points? My sample set is 5 points. Chills as yes, I have 1, 2, 3, 4, 5. 5 samples of chills as yes. Sorry, 5 samples of flu as yes. How many examples of no? So I have 1 example of chills as no, 2 examples of chills as no. So my answer should be 2 divided by 5. Okay, I hope you get this. Let me clear this mess. Ask you the next question. What is the probability of this term? Chills as yes and flu as no. Okay, chills as yes and flu as no. Many of you are saying 1 by 3. So let me verify. Yes, I think you're right. The number of terms that I have in the denominator will be 3 because I have 3 terms of no. How many of these 3 are yes? So I have 1 yes, no, no. So I have 1 example of yes. So chills as yes and flu as no is 1 by 3. What is the example of this? Chills as no and flu as no, 2 by 3. Excellent. So I hope you are able to now evaluate all of these terms. Okay. Let me just randomly pick again one of them. So let me say this example. Okay. So for this example, I am asking, what is the probability that headache is mild? Okay. Headache is mild and chills as yes. Okay. Let me color this out. Headache is mild and chills as yes. Can you evaluate what is the number here? Okay, I'm getting many 2 by 5s. 1 2 by 3. I'm also getting 2 by 4. Okay. Okay, since I have some different answers, since I am having different answers, let me explain how this looks like. So what should be on my denominator? So chills as yes, my denominator should be 5 because there are 5 examples of chills as yes. Now within these 5 examples, how many examples of headache as mild? So I have 1 example of headache as mild and 2 examples of headache as mild. Okay. Yes and headache mild. Yes and headache mild. That's it. Only 2 examples. So I get 2 by 5. Okay. Let me do one more. Can you try to evaluate this term? Fever as yes and flu as yes. Okay. Okay. put fever as yes, flu as yes. Actually, it should have been no, but fine. Fever as yes, flu as yes. I'm getting 4 by 5, 3 by 5, 4 by 5, many 4 by 5s. Okay, let's look at here. Flu as yes and fever as yes. So I have 2 examples here and 2 examples here. So 4 favorable conditions, 4 divided by 5. Okay, excellent. So I hope many of you are now at least clear in evaluating these terms. Okay, let me go to my next slide where I have already evaluated these answers. Here I have done a mistake actually. This should be fever as yes and flu as no, because this entire column is for no. But apart from that, these are the terms that we can evaluate. Okay, these are the individual probabilities that we can evaluate. Now we are not really interested in these individual probabilities. What we are interested in is we are interested in evaluating this test term. So for this test term, we see that what is the probability that I have chills as yes, runny nose as no, headache as mild, fever as no. What is the probability that I have flu? So I have 2 examples. Okay, one is when flu is yes, the other is when flu is no. Sadly, while editing this slide, I have copied this part on my answer, so I have not evaluated it. But let me do the first part, and the second part I will verify from my slide and get back to you. Okay, so turn this on. Okay, so what is the probability that flu is yes and for a given data? What is the probability that given a data I say that flu is yes? So I can evaluate that. Okay, so my probability is the probability that flu is yes given data is equal to the probability of data given flu as yes multiplied by probability of flu as yes, right? This is what Base Theorem told us. We also have a denominator, but we know that the denominator is not important. Even if I don't evaluate the denominator, still I can get a fairly right answer, okay? Because I want to compare between 2 terms. Now, in the first part, the probability of X data given flu as yes will be divided into multiple parts. I will say the probability of chills as yes multiplied by the probability of runny nose as no multiplied by the let me see that again. Probability of chills as yes and flu as yes. Probability of runny nose as no given flu as yes. Probability of headache as mild given flu as yes. Probability of fever as no given flu as yes. And all of this multiplied with probability of flu as yes. Okay, and this evaluation of this formula will help me evaluate this term. Probability that I have flu given this data is the probability of chills being yes. Okay, this column is for chills. Chills being yes and flu as yes. Runny nose being no and flu as yes. Headache being mild and flu as yes. Fever being no and flu as yes. Okay, so multiply all of these conditional probabilities together with the prior probability of flu as being yes, and we'll get our answer. So now we have our table. I can say first part, probability of chills as yes and flu as yes, which is this term. Probability of chills as yes and flu as yes, 3 by 5. 3 by 5 is 0.6. So I say the first term is 0.6. Next term, probability of runny nose as no and flu as yes. So runny nose as no and flu as yes. This term, 1 by 5. 1 by 5 is 0.2. So instead of this, I put 0.2 here. Probability of headache as mild and flu as yes. So headache as mild, flu as yes. 2 by 5. So I put 2 by 5 here. 2 by 5 is 0.4. I get 0.4. Probability of fever as no and yes, flu as yes. So fever as no, flu as yes, 1 by 5, which goes here, which is 0.2. All of this multiplied by the probability of flu as yes. Probability of flu as yes is 5 by 8, which is 0.625, which comes here. So when I take all of these terms and I multiply it together, I get 0.006. That means the probability of having flu given this data is 0.006. Now we also need to evaluate the second term, right? The probability of having flu as no given the same data, which will be evaluated as, I can take the same thing I've written here. Sorry. Make a copy of it. Paste it. It will not fit, so I make it a bit smaller. Okay. So I can evaluate using the same formula. Okay. But within this formula, I will have to change certain things. I will have to say, instead of yes here, all of these guys are supposed to be no. Okay. Probability of chills as yes, flu as no. Runny nose as no, flu as no. Headache as mild, flu as no. Fever as no, flu as no, and flu as no. So here also I can take these terms that I have here, put it into this formula and get this number. So I have, as I said, I have hidden this number, but let me just say that we evaluate this and we get the answer as 0.038. Okay, let's say we get the answer as 0.038. So once we have these two numbers, what is the probability that this test data gives us flu or not flu? Probability of having flu is 0.006. Probability of not having flu is 0.038. So I would say no for this answer. Does that make sense? Okay. Let me summarize what we have done. We have seen the individual ways, we have seen from a given data how to evaluate the prior probabilities. We have also seen from this data how to evaluate the conditional probabilities for each of the feature and the given condition that we know that they have flu or not. Once we have these probabilities, we can then evaluate this term. How we are evaluating this term? We are evaluating that term using our Base Theorem. Okay, Base Theorem says that this term, that is the probability of a class given data, is equal to the probability of data given class multiplied by probability of class. Now, probability of class is easy to find. Probability of data given class, we will say that instead of this, we will go here and we will expand this formula to the product of individual features and that class. The problem is, to do this term, this formula is only valid if the features are mutually exclusive. If the features are not mutually exclusive, then this formula may or may not be true. Okay. But since we are not testing and we are assuming that this is true, we call it naive. Once we assume it's true, then we can evaluate these terms. Once we evaluate these terms, we can evaluate our final formula and we get these numbers. And based on these numbers, we can predict from naive Bayes whether naive Bayes says yes or no, depending upon what is the number. Okay. I hope you have understood naive Bayes. Let me give you a few advantages and disadvantages. The advantages are, in the training phase, I can evaluate these probabilities. In our case, how many probabilities are there? So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 10. We have 20 numbers, 20 parameters that we will be learning from our data. Okay, these 20 parameters we'll be learning from this data. The data that we have, we call this trained data. from these trained data, we'll be learning these numbers. Once we have learned these numbers, then for our new data, our prediction data, we can use these numbers to evaluate, to calculate a number, and based on that number, we can evaluate the probability and then give the prediction. Okay, so for KNN, the number of parameters that you have to learn, the number of parameters that you have to remember or evaluate depends upon the size of the data. Okay, if I have 1,000 training points, I have to evaluate 1,000 distances. If I have 1 million training points, I have to evaluate 1 million distances. For naive Bayes, for 8 training points, I have to evaluate 20 parameters. For 1,000 rows, also 20 parameters. For 10,000 rows, also 20 parameters. For 1 million rows, also 20 parameters. So the number of parameters do not scale with the data. Okay, even as your data increases, the number of parameters that you will want to go for remains the same. Okay, so that basically means that for very large data sets, naive Bayes will work very nicely, because it will take the same amount of time to evaluate the prediction whether I have 1 million data points or 1 data point. Okay, now evaluating this terms, getting this value here is also very easy. You see, within pandas we have seen many selection criteria, right? If this is a pandas data frame, I can very easily choose, or by just writing one line, I can know one of these terms. Okay, by writing one of these lines, I can write one of these terms. I can either use group by, or I can use some kind of filtering examples. So I can choose my favorable conditions and my total number of conditions very easily. So naive Bayes is actually very easy to implement, and it works very well for large data sets. So these are the advantages. What is the disadvantage? So disadvantage or con of naive Bayes is we have made an assumption. Okay, we have made a naive assumption that to evaluate the probability of data given a class, I can say that the probability of the individual features given a class, I'll multiplying them together. That's a naive assumption, because that assumption is true only when the features are mutually exclusive, or only when the features are not correlated. But if the features are correlated, then this formula is wrong. So what I mean by correlation? So we know that when someone has flu, it is very likely that they have fever. It is very likely that they may have a headache. It is very likely they may have a runny nose, or very likely they may have chills. That means that these are not independent features that link with flu. They are very much dependent upon each other. Okay, if I have fever, maybe I also have a headache. Okay, let's say if I have to give a number. Okay, if I have fever, there is probably an 80% chance that I will have, maybe a 40% chance that I will have mild headache, and a 60% chance that I will have strong headache. Okay, so what I'm doing now is I am linking the correlation between fever and headache. Okay, and if this correlation exists, okay, if there is some correlation between fever and headache, then we cannot use this formula. This formula is not valid. Okay, but naive Bayes still goes ahead and uses this formula, and that is when naive Bayes will fail. Okay, if I have features that are highly correlated with each other, naive Bayes will not give us a very good solution. Okay, I hope this was helpful, that we were able to take a basic algorithm like naive Bayes, go to the base, that is understand what is Base Theorem, understand what is conditional probability, take an example of a simple data set. This is of course a fake data set. Okay, this data set does not have any meaning, but it helps us to evaluate, or it helps us to learn how naive Bayes would work in the background. Okay, in a true sense, we will never be using we will never be implementing this naive Bayes. We can directly use a method from scikit-learn that helps us to solve this problem. Okay. So with this, we'll stop today. In tomorrow's class, we will look at decision trees, and hopefully we'll also look at something called as random forest. Once we have done that, I think then we can go to seeing the evaluation methods, that is validation, cross-validation, and so on. and finally implement all of this into our Titanic example. Okay. So let me stop here. I am already late for my meeting. Okay, Nirja ma'am, I'll exit now. Okay. Okay. Great. Have a good day. Bye bye.